All right, Unit 3 is on derivative rules. There are rules to these derivatives. There are rules to finding derivatives. I'll tell you what I'm talking about in a second. There's 4 lectures, and then we'll have a review day, then a test day, just like the last unit. Now, I'm giving you 3 functions, f, g, h, and k, and I want you to sketch the derivative functions of each. It does not have to be exact. It's just a sketch. It'd be great if we could find exact slope values, but let's just do a decent sketch using, a couple x values, figuring out if your slopes are positive, 0, or negative, and then plotting them on the corresponding f prime graph. Now, the functions I give you are forms of like a linear equation, a y equals mx plus b equation. Second one, I gave you a form of an x squared equation. This is some sort of quadratic. Then some sort of cubic. I'm not giving you the specific formula for it. I'm just telling you it's something to the 3rd power as your highest degree. And for the last one, I'm giving you something to the 4th power. Now, for the second guy, we have a negative slope, a less negative slope, a 0 slope, positive, more positive. So at those x values, I will graph a negative, a less negative, a 0, positive, more positive. I do the same for h and for k. Whoops. Positive slope, a 0 slope, a negative slope, a 0 slope, positive. Should all be able to do this. Just look up to check. Yeah, it's curvy. And then k, let's add a couple extra points in here. One, 2, 3. Negative, 0, positive, 0, negative, 0, positive. 1, 2, 3, 1, 2, 3, negative, 0, positive, 0, negative, 0, positive. We should all get graphs like that. Do we notice anything? What do you got, Miss Coffee?
The derivative is like the 1 to 3 less.
Exactly. The derivative of this x to the 4th is like an x cubed graph. Exactly what kind of x cubed graph, I don't know, but it is like an x cubed graph. The derivative of this x cubed was like an x squared graph. The derivative of the x squared was like x. The derivative of this y equals mx plus b was just a number. Well, mathematicians kind of saw that and saw this consistency. And it's consistent as you look on further and further and further. And they use the definition of the derivative, which we know, to develop rules. They kind of showed proofs that if you have this type of function, the derivative will always be this. And instead of using the definition of the derivative, they're like, you know what, let's use these shortcuts. What do I mean by that? To find our slope generator function, say of f of x is equal to 3x squared plus x. Before you use the limit definition, and you plugged in 3x plus h squared plus x plus h minus the function all divided by h. And then you worked your way, simplifying it, doing all this algebra, canceled a bunch of stuff, factor out an h, cancel the h, and you developed that this derivative was 6x plus 1. Well, now we will just take this function. We will use rules, and we will say the derivative is just 6x. Sorry, this is plus x plus 1. And the first rule we'll talk about is this power rule. If we have something to a square or to a power, we would be able to subtract 1 to get our derivative. And we'll talk about how you have to worry about a certain constant as well. But the simple one is if we have just a power, say this is to the first power, this is just 1, well that's like x to the 0th power. Now you're probably wondering, why did we learn this in the first place, Mr. Mester, when there's all these rules that'll make this a lot easier? Well, we kind of have to appreciate where the rules come from. Okay, these things don't just come out of thin air. It comes from this definition. And if you look in your book, there will be proofs of take x to the n, take the derivative of it, and boom, they get this, the rule that I'm about to introduce to you. So that's one reason. You have to understand the rules all come from the definition of a derivative, which isn't this, but it's, f of x plus h minus f of x over h. Also, we need to be familiar with this formula, this limit definition of a derivative. Because in the future, you're going to be asked to find this limit. And you're not going to be able to find that algebraically like we did last unit. Instead, you're going to be like, oh, if f of x is log x, what is f prime of x when x is 2? And you'll be able to generate the derivative. And there's a rule for the derivative of log x. We're going to use the rule to find that derivative. It's just 1 over x. This would just be 1 over 2. Okay, but we'll talk about that derivative of log x later. Right now, we're going to worry about this power rule. We'll have the derivative of x to the n. But before that, I need a quick notation heads up for taking a derivative. What is the operation to take a derivative? Yes, but there is a mathematical notation. Okay, if I have say, some function. I don't want to do that. The notation to take a derivative is the following. D dx of whatever. Now, it's kind of D, but it's kind of not a D. What this means and what this D is the notation kind of similar to the delta, only it's the instantaneous change. Delta is just change. This D is instantaneous change. And you'll see it like this, but most likely people use just the letter D because they can't find this symbol. I believe it's a Greek symbol in their computer. So you see just the letter D. Okay? Now this would mean this is the instantaneous change of whatever you have here over the instantaneous change of x. Now it doesn't have to be x. But just like slope is change in y over change in x, a tangent slope would be the instantaneous change of y over the instantaneous change in x, or the slope of 2 points infinitely close together. So what we're going to do, if I ask you to take the derivative of, say, 3x squared plus x, you'd say take the derivative of, y, or you could have f of x. Let's start with f of x, which is 3x squared plus x. And you'd say, well, the derivative of f would just be f prime. That's the only really notation we use to show that. And we find out that this is 6x plus 1. So this is take the derivative of this function with respect to x. Now, a couple other things. We could have different variables, say w's and z's. I could have w is equal to 3z squared plus z. What I would do is I'd take the instantaneous rate of change of this function, but instead of x's, I could use z's and say find the instantaneous rate of change of w with respect to the instantaneous rate of change of z. And what you do when you take the derivative of w with respect to z is you get the instantaneous change of w with respect to z, or dw dz. That's another way of writing w prime. And it's the same deal as 3x squared plus x. This would be 6z plus 1. Okay, and I could do, y's and x's. Y is equal to 3x squared plus x. I would take the instantaneous rate of change of that function y with respect to the instantaneous rate of change of x. This would give me either dy. It's kind of like multiplying by a fraction. This is d times y over dx times 1. And that would be 6x plus 1. And dy dx is another notation for just y prime. And you're used to using, f prime. All just different notations we have to be familiar with. Okay? Let's get to this first rule of derivatives, the power rule. You don't really need this statement if you don't want it. It's just more of a, if x of x to the n is differentiable, and really the power rule is, if you want to take the derivative with respect to x of x to the n, you will take your exponent and move it in front of the x, and then you will subtract 1 from your exponent. That's your first rule. That tells me that the derivative of x squared is just 2 times x to the 2 minus 1, which is just 1, which gives me the derivative is 2x. That kind of makes sense based off the pictures that we were going with. I had a quadratic function. The derivative looks like a linear function. But it's a linear function with some sort of constant involved. It's not just the derivative of x squared is x. But it's a nice simple rule where it's just 2x. Now let's, you guys will do this one. I'll show you this guy, x to the square root of x. If I have the square root of x, I should know that I could write this as x to the 1/2. So if I want to take the derivative of the square root of x, I would just bring down my exponent and then subtract 1 from my exponent. That would be 1/2 x to the negative 1/2. If I have a negative exponent, it's the same as the thing with a positive exponent, just the reciprocal of it. So if it's in the numerator, I put it in the denominator and make the exponent positive. So this would be equal to 1 over 2 x to the positive 1/2, which is the same as the square root of x in the denominator. Okay, you guys do the next two. Do this guy and do this guy. Now, I'm not taking the derivative of an equation. It's just an expression, which is why we don't have like y prime equals or f prime equals. We should know that the cubed roots can be written as x to the 1/3. It can, but it's good to be able to rewrite it. Now, we get 7x to the 6th for the first one. Nobody has problems with that. If you have problems, it's okay. Just we'll get comfortable with this. Now, the second one, most people are kind of worried about the notation. I'll show you all the different ways you can write the derivative of this. First thing, we rewrite it as x to the 1/3. Sweet. Now we take the derivative. So I'm going to move the exponent down and then subtract 1 from 1/3. Now, subtracting 1 from 1/3, that's like subtracting 3/3. So I'm subtracting 3/3 from 1/3, I get negative 2/3. So I get 1/3 x to the negative 2/3. You can write this the following ways. This as well. You can write it as what you have here, or 1 over 3 x to the 2/3, or 1 over 3 cubed root of x squared or 1 over 3 cubed root of x. Oops, let me make that a little nicer. Cubed root of x quantity squared. Okay, which way do I want it? Don't really care. What's going to be important is for you to know how to change this into the 2/3. Okay, now why is this the same? Because what you're doing is you're taking like, gosh, I'm sorry, I've run out of space. Let me get rid of this. What this is really essentially is x squared to the power of 1/3. When you have a power to a power, you multiply your powers. That makes it 2/3. And your other guy, you have the cubed root of x quantity squared. That's x to the 1/3 quantity squared. So either way you write it like this, you get it to 2/3. Do you have to put your answers like this? No. I'd like you to make the negative exponents positive. I think that's a good thing to do. But besides that, you're cool to leave it as 2/3. Okay? But when you're plugging in values, like I might ask you what this is when x equals 8, you'll need to know how to take 8 to the 2/3 power. And the only way I know how to take 8 to the 2/3 power is by splitting it up and say, okay, the cubed root of 8 is 2, 2 squared is 4. So you got to know how to transfer this 2/3 power into this power of a power. Does that make sense? Anybody have any questions about that? Didn't want to confuse you with that too much. Okay. Talk about the derivative of a constant. You can kind of develop this rule by thinking of the power rule, but I don't like to think of the power rule when I'm dealing with just this constant. Who knows this derivative? And maybe a reason why. 0. Good guess with the 1. Why is it 0? Exactly. You think about a line. It's the easiest way to think about this reason is that if I have a line, k, well, that's a y equals k line. That's a horizontal line. Slope is always 0. So if I take the derivative of 7, that's 0. The slope of the line, the function 7, is 0. Well, kind of the same thought process can be used for the derivative. And you can see d's or you can see stuff like this. It's the same stuff of just x. What do we think that is? That's 1. You can think about the line, y equals x. The slope is all 1 everywhere. Well, thinking about x brings us to the constant multiple rule. If I have 6x, what would be the slope or the derivative of 6x? What's the slope of the line y equals 6x? What's the tangent slope? It's just 6. What if this was 2x? 2. Well, the way to think about that for any function, this is 2, is I'm taking the derivative of some constant times a function. Sorry, that's just f. You can just leave the constant alone and multiply that by the derivative of the function. So if you think about 2x, the derivative of x is 1 times 2 is 2. Which brings us to like these, the derivative of 4x to the 7th. That's going to be important now. I'm not showing you the step that you need to take to find the derivative. If I just give you the function, I'd expect you to say, okay, take the derivative with respect to x of this entire function. Some teachers require students to do it on both sides. I'm not that picky. As long as you put your parentheses around everything, I'm cool with that. Now, the derivative of y with respect to x, it's almost like multiplication. It would be dy dx, or the instantaneous change of y with respect to x, which is the same as y prime. You can use y prime if you want. Well, you would leave the 4. You'd multiply the 4 by the derivative of x to the 7th, which we talked about is just 7x to the 6th. This derivative is just 28x to the 6th. Multiply the 4 by the 7, subtract 1 from the exponent. Okay, you guys do the other two. And I don't want to write just 28x to the 6. I would probably write y prime is equal to 28x to the 6. Because you're taking the derivative of y equals. Remember, bring the exponent down first, and then subtract 1. Multiply the 6 by 1/2 before you subtract 1. But you didn't multiply the 1/2 by the 6. It's almost easier to not even do this middle step. It's almost easier to just go 7 times 4 is 28. Subtract 1 is 6. After I would rewrite this to be x to the 1/2, I would do 6 times 1/2 is 3. Subtract 1 from 1/2, I get -1/2. You get 3 x to the -1/2. Of course, I'm taking the derivative of this, giving me f prime is equal to 3x to the -1/2, which is the same as 3 over root x, or 3 over x to the positive 1/2. Okay, the final one is what, Mr. Owusu? -3 over 2 times x. What's the derivative of x?
Sorry, I'm completely blank.
What's the derivative of x?
1.
Okay, so -3/2 times the derivative of x is -3/2. Thank you. Okay? Not too tough once we get used to it and once we practice it. Okay, notice I'm writing it as an equation. Now, these rules, remember what they're getting you. They're giving us these derivatives. What are these derivatives? Tangent slope generator functions, okay? It's beautiful to just be able to apply the rules, but it's even better if we can understand what this means. This that I just generated is all of the tangent slopes to f, no matter where we're looking at. I can plug in any x value, and I'll get the tangent slope of that function, okay? We are developing tangent slope generators. Don't forget that. Of your original function. It's easy to forget that. I'll be able to plug in x values into those derivatives to give me slopes of my original equation. Now, let's look at f of x is equal to 1 over x squared, and we want to take the derivative of this. I will tell you right now that the derivative of this f prime is not 1 over 2x. The power rule does not work if your variable is taken to an exponent in a denominator, if it's in a quotient. Okay? The power rule only works when you have your x to a power in a numerator. Only works when x to the n is in a numerator. Well, what can I do to 1 over x squared to put something in a numerator? Exactly. The rules of exponents say if I take a negative exponent, it'd be the reciprocal of the positive exponent. So if I have x squared in the denominator, that's the same as x to the negative second in the numerator. Well, now I can use the power rule to say that f prime is equal to negative 2x. Now, negative 2 minus 1, negative 3. Make sure you don't say that's negative 1. Adding a negative 1. So that's the same as negative 2 over x cubed, which is entirely different than 1 over 2x. Okay. So let me show you one more, and then you'll do the rest. I have, this is 2 over x. I would rewrite this as 2 times x to the negative first, then taking the derivative of everything with respect to x. I would say f prime is equal to negative 2 x to the negative second, which is negative 2 over x squared. Okay, try to move all of your negative exponents so that they're positive. The simplification of the fractions to make it like roots and to the powers, not necessary. But I would like all the negative exponents to be positives. Okay, so do those other three. That's 4 over 5t squared. Now, to take the derivative of this g using t's, you would take the instantaneous rate of change of that g with respect to t. Your answer should be either dg dt or g prime. Both are acceptable.
Would it be g prime of t?
It would be g prime of t, exactly. Because this should be like g of t. Right now it's just g equals. Good. Okay, do that one. And do the other ones as well. Now, I would write this most likely as the fraction 4/5 times t to the negative second. You don't have to move t up to the numerator, but you can, fine. But maybe you just think of 4/5 as being just a number that you're going to be multiplying by negative 2. Check your answers with a neighbor once you're done. Yes. Questions? Anybody have any issues while we're doing these? Would like me to check their work if they have a neighbor that's mean to them and doesn't want to check with them? Because we should be checking with our neighbors.
I'm working on it. I got it. I can do it. I can do it.
Let's go. You don't learn math by looking at it, Miss Wheatley. So, the cubed root of x squared. You can write that as x squared to the 1/3. So that's like x to the 2/3. Oh yeah, that kind of looks like that. Yep. 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 Fine. You know that, right? As long as it's not a multiple choice question, you can leave it unsimplified. It's the same thing. So third one, I rewrote 7/3x cubed. This one. Okay. So this is the cubed root of x squared. So the cubed root of x squared the cubed root of x squared is the same as x squared to the 1/3 power. That is the same as x to the 2/3. Do we get that at least? That's important. Once we understand that, okay, we rewrite this as 1/2 times x to the negative 2/3. Then multiply the 2/3 by the 1/2, that's negative 2/6. Subtract 1 or subtract 3/3 from the negative 2/3, that's negative 5/3. The negative 2/6 can be simplified to be negative 1/3. The negative 5/3 can be brought down to the denominator, be x to the positive 5/3.
So can that also be like 3 cube root of x to the 5th?
Yes.
Okay.
Or the cubed root, no, yes, the cubed root of x to the 5th. It's both ways can be written. Okay? All right. Brings us to our next rule. This is such a beautiful rule, you'll take it for granted. If we have the sum and difference of functions, let's say f and g and h and whatever functions I use are differentiable, it means you can take the derivative of it. Then the derivative, and I'll use these fancy d's sometimes, I'll use regular d's the other times, it's the same thing, of this f plus, or could be subtracted by this g, plus or minus this h, et cetera, et cetera, et cetera. It's just f prime plus or whatever minus g prime plus or minus h prime forever and ever and ever. So giving you a quick example of that, if I wanted to take the derivative of y equals 3x cubed plus 2x squared minus x plus 5, I would get dy dx, or y prime, is equal to 9x squared plus 4x minus 1 plus 0. However, this is just a sum and difference rule. It is not a multiplication and division rule.
Can you go over how you spell that? Yeah.
What's the derivative of 3x cubed?
Oh.
9x squared, right? What's the derivative of 2x squared? 4x. Derivative of x, 1. Okay? That's all. Yeah. What's the derivative of 5? Plus 0. Okay? It does just disappear. But we have to know why, because the derivative of 5 is 0. Does not work for multiplication or division. There are special rules for multiplication or division that we'll have to get to and talk about. And you will have questions that will have multiplication and division in them, and you'll find ways around it. I'll show you that in a second. But let's do this. Now, I could ask you these questions a different way. I could ask you to find the instantaneous rate of change of the function at x equals 1, or if you have z's, z equals 1. Let me tell you what I mean by that. You have to take the derivative, and you're going to, well, essentially you're going to find the instantaneous rate of change of the function. You know that's a fancy word for the derivative of the function, which is the fancy word for the slope of the tangent of your original function. Just you're going to find it at a specific point. I'm going to find the slope of this function, the tangent slope of this function, when x is 1. How do I do that? I find the derivative. Step 1. The derivative of this guy, it's negative x to the 4th over 2. Well, I can rewrite that as negative 1/2 x to the 4th. Let me move this down. The derivative of negative 1/2 x to the 4th would be negative 2 x cubed plus the derivative of 3x cubed would be 9x squared minus the derivative of 2x is 2. That is my tangent slope generating function. I want to know what the slope of the tangent of my function is at 1. I plug in 1. Negative 2 plus 9 minus 2. That's 9 minus 4, which is 5. Which is crazy, but turns out this quartic function at 1, its tangent slope is 5. Cool. And if we graphed it, we'd be able to kind of see that in our graph. We'd have a positive slope. It'd be equal to 5. Eventually, we'll be able to use our calculators to find the derivatives of the function anywhere we want, but not yet. So do these two. Actually, just do this one. We'll skip this one, unless you already wrote it down. But we got to move on. Let me not erase. Find the instantaneous rate of that function when z is 1. The correct notation for taking the derivative would take the instantaneous change of w with respect to the instantaneous change of z, or dw dz. Which is the same as does w prime, if you want to use that. And I get 20. This is a 2, not a z. My z's I put lines through. The derivative of negative 5 over z squared, I'd write it as negative 5 times z to the negative second. That would turn into a positive 10 over z cubed, or positive 10 times z to the negative third. The derivative of 5 is 0. You could put a plus 0 there just to make sure you know. So I get 12z squared minus 2 plus 0 plus 10 over z cubed. Find this derivative when z equals 1 to find the slope of this function when z equals 1. It's equal to 20. Very steep. Well, comparatively to 5, it's steep. But to other things, it's not that steep. Okay? Cool? All right. What about the derivative of 2x to the 5th squared, or the derivative of this? We're going to do both of them. What do you think we have to do for 2x plus 5 quantity squared? We'd have to distribute it all through. We'd have to FOIL it. And we'd have to take the derivative of this. Okay? So don't get tripped up on that. We just get 8x plus 20 as our derivative. What about this guy? I will tell you right now, this derivative is not 3x squared plus 2 over 2x. Wrong. You can't use the power rule if you have x's in a denominator, especially when you have two things being divided together. So what do you think we have to do so that we can use the power rule, Mr. Interconnect?
Take out like the 1 over x squared separate from the x.
That actually would not help me because this quotient turns into a product. I'll tell you this right now. You're not going to have 3x plus 2 times whatever the derivative of x to the negative second is. So that actually doesn't help me, but it's a good idea. Any other ideas? Mr. Kaiser? How do you simplify? No. Split this into 3 different fractions. X cubed divided by x squared is just x plus 2x divided by x squared is 2 over x minus 5 over x squared. Now you take the derivative of that, and I'll do it quickly, it'll take you longer. You get 1, you get negative 2 over x squared, you get positive 10 over x cubed. Okay, but of course you would rewrite this as x plus 2 times x to the negative first minus 5 times x to the negative second, and then you would find the derivative.
I'm not right. What we did, was it as plus that is times 4, or that was times 2?
So what do you mean it was times 4?
Well, the original is 2x plus 5 squared, and then the other one is like 8x plus 20. So that's just like the inside of the term 2 times 4. Was that just plus?
Yes. There is a rule, a chain rule, that you'll see why it's the inside times 4, but it's not always going to be that case. And there won't always be like constant times the inside. It'll be a little more complicated than that. Okay, chain rule. Mr. Jesperson.
So when x is in the denominator, are you basically just multiplying by the negative exponent and then adding them?
Yeah, because you think about moving it up, and this is negative 1, so you're going to multiply by the negative of it, making that negative 2, and then when you subtract 1, that makes it negative 2, so you are kind of just adding 1 when you subtract 1 from a negative. So here, negative 2 times negative 5 is positive 10, so you multiply by the opposite of this, and then you add 1. Yeah, you could kind of create that rule if you want to. Just don't make mistakes with it. That's fine. Now, because we know all these rules, we'll have applications and questions that we can do quickly now. So this was a test question. Everybody took the test in here, right? Okay. The test question, 27, 28, 29, and 30, or 28, 29, and 30, was this. Find the equation of the line tangent to f of x equals 2x squared plus x minus 3 when x equals 2. Well, you know, for your equation, you need a point and you need a slope. Where do we get our point from? The original function, where our tangent line will pass through. Where will we get our slope from? Our slope generator, our derivative. Well, guess what? We can find f of 2 quickly, just like you did. That's 8 plus 2, which is 10 minus 3, which is 7. So I got my point 27. Well, what took you an entire page of work on your test now takes you 2 seconds. Come on, Mr. Messner. You could plug in 2 into that to get your slope of your function when x is 2, that's 9. You have the answer to your test question. Like that. Okay? We go to 26. Oof. All right, we're going to have to watch some video when we get home. We'll see. Find the equation of the line or lines. Let's just find the x coordinates. Of the lines tangent to x cubed minus 3x squared that are parallel to the line. This is positive 9x minus 2. Figure that out. Go. If it's parallel to the line y equals 9x minus 2, I want to figure out when the slopes of the tangents of this equal 9. How can I figure out when the tangent slopes are equal to 9? Let's find the derivative, which is our tangent slope generator. Plugging in values for x would give me my slopes. If you want to start guessing and checking, sure, maybe you can find 9 by plugging in random values for x. But an easier way to do this is to find and to discover the values of x by setting this tangent slope generator equal to 9. And seeing for what values of x will my tangent slope equal 9. Now we have a quadratic, x squareds and x's. Move everything onto one side to solve. Factor out of 3. And then factor to solve this product set equal to 0. Next question. Find the x values where the function has a horizontal tangent. What is a horizontal tangent? Slope is 0. Perfect. A horizontal tangent line, like something like that, horizontal, slope is 0. All we need to do is figure out where the horizontal tangent slope equals 0, or where the tangent slope equals 0. Find the derivative. That's my slope generator. Set it equal to 0. When x is 4, we'll have a horizontal tangent. what we'll discover in the future, that will be a location of a critical value, like a maximum or a minimum or stuff like that. Same thing goes for here. I'm going to come back to this problem. We're going to do this problem first. What you won't hear now, which you will hear on the video, is I'm going to go through the derivatives of sine and cosine. It's actually not that hard, but it'll be stuff that you'll have to remember. It's easy. Just watch the last like 15 minutes. Let's talk about differentiability. We'll end class with this. Function is differentiable we've already kind of talked about this. If it is continuous, and the slopes from both sides are the same. Slopes of the tangents. Okay, the left-hand slopes have to equal the right-hand slopes, and we have to have continuity. This is why at sharp points at cusps, we are not differentiable, because the slopes from the left and the slopes from the right aren't equal. Well, we're going to see a question like this now, which we couldn't do before, but now that we have these rules, they're easier to do. Yeah, sure. We are trying to find a and b such that the function f is differentiable everywhere. Hold on, let me get through this problem. For a function to be differentiable everywhere, it has to be continuous. So, from the left and from the right, we're going to have to be equal to the same value at x equals 2. Also, the tangent slopes from the left and the right are the same. And we'll look at x equals 2 in this situation. So what I do is I plug in 2 into both for the continuity. I say 8a would be equal to 4 plus b. That's my first equation generated. Now the tangent slopes from the left and the right of 2 have to be the same. I will take the derivative of both of these, d dx, giving me 3a x squared. Take the 3 down, multiply it by a times x squared. And then the bottom one, the derivative of x squared plus b, is just 2x plus 0. The derivative of b is 0. Now this is going to be at x equals 2, so 3a times 4 is equal to 4, or 12a equals 4. A equals 1/3. Once we know what a is, I can plug in to find b. Okay? Thank you for waiting. I'll see you guys on Tuesday. Watch the rest of the video to help you on some homework problems.
We said to talk to you about our test if we didn't like where we were.
I'm so proud of myself.
Okay, let's do this problem. Find a and b such that this function is continuous everywhere. Well, two things we need to make sure happens. We need to be continuous, and these pieces need to be continuous at x equals 1, and the slopes have to be the same, or we have to be differentiable. The derivatives have to be equal. At x equals 1. So let's check continuity. I'll plug in 1 into both functions. I get 3 minus 1 equals a plus b. or 2 equals a plus b. Step 2, my derivatives from the left and from the right have to be the same at 1. So I take the derivative of 3 minus x. The derivative of 3 minus x is just -1. The derivative of ax squared plus bx would be 2a times x plus b. Now, of course, I have to plug in 1 for x, so this is just 2a plus b. Now I have 2 equations, 2 unknowns. I have a system that I can solve. Stack them on top of each other. I'll multiply one of these equations by -1 to create opposite b's. Let's go ahead and do it to the bottom one. Add the equations together. I get 3 is equal to -1a, which means a is equal to -3. Once I have a, plug it into either original equation that you generated, and you'll find b. Okay, so that's a, that's b. That's how you would do a question like that. You'll have a question like that on your homework. 2 questions like that. Now, this is a tough question. Find the line, or find a k such that the line y equals 4x minus 9 is tangent to the function of f of x equals x squared minus kx. Okay, so for this line to be tangent to this, well, this equation, or like the y value at some x value, will be equal to the y value at the same x value. So the first thing I can do is I can say, okay, well, x squared minus kx has to equal 4x minus 9 for some x value. This will help us find k. Now, the second thing I need is I need to know that the slope of this line, 4, will have to be equal to the tangent slope of this line, which will have to equal 4 at some location. So if I take the derivative, I get 2x minus k, because the k is just a constant. It's not a variable or anything. Well, that equals 4 for some value. Now, I could solve this for x and then plug in k's wherever I see x, but it'll actually be a little bit messy. So instead, I'm going to solve this for k. And I get what k is equal to. So now I can actually use this k and plug it into my kind of equaling of the 2 functions, because I know that for some y coordinate will be equal to the same thing on a specific x coordinate. So take that k, plug it in, I'll get x squared minus 2x minus 4 times x is equal to 4x minus 9. And hopefully once I find x, I will find k, because k has got to be equal to 2x minus 4. So I have x squared minus, this would be the quantity of 2x squared minus 4x, which is 4x minus 9. I will then distribute the negative, subtract 2x squared, I get negative x squared plus 4x is equal to 4x minus 9. Subtract 4 x's from both sides. Negative x squared is equal to -9. Multiply by -1, I get x squared is equal to 3. X squared is equal to 9, which means x is equal to plus or minus 3. Well, that means there are going to be 2 locations that I'll have for k. I plug in 3, I get 6 minus 4, which is 2. And I plug in -3, I'll have -6 minus 4, which is -10. So that means there will be 2 types of quadratics that this line will be tangent to. And it kind of makes sense if we can look at things graphically. If I have the line 4x minus 9, Let's kind of sketch it 4x minus 9 here. Well, if I have a function that could look like this, that'd be tangent. And maybe I have another situation where it's tangent higher than that. Okay, we could actually have a lot of quadratics. Not necessarily 2, but in this case, when it's just x squared minus kx, there are just 2, which is cool. Okay, so that's that. Now let's talk about the derivatives of basic trig functions. Here I have sketched the graph of the sine of x. Sine of x is in black. I'm going to sketch in red f prime of x. And I'm just going to do it right on top of it. And to do that, at all of these important values, I'll kind of sketch the tangent slopes. And then I'll sketch the derivative values, the tangent slope values. So if this is f, here comes f prime. We have a positive value. It's actually 1. This is a 0. This is a negative. This is a 0. This is a positive. 0. Negative. 0. Positive. And if I sketch that graph, let's go ahead and just turn it into blue so that we can see it better. I get this graph. Now, what is this a graph of? Well, let's think about it. If I plug in 0, I get 1. If I plug in pi over 2, I get 0. If I plug in pi, I get negative 1. You should be thinking, okay, 0, 1, pi over 2, 0, pi, negative 1, that we have actually the cosine function. We just found the derivative of sine by sketching it. The derivative of sine is cosine. Cool. Well, let's look at cosine, and let's do the same process. Let's sketch the graph of f prime if f is cosine. So here was the cosine function that we just developed here in blue. Just I put it down here, it looks a little nicer. That way we can kind of separate it. And let's go ahead and start sketching. I got 0, negative, 0, positive, 0. And here we have negative, 0, positive, 0. So let's do it. I'll do it in blue. 0, negative, 0, positive, 0, negative, 0, positive, 0. Sketching it, connecting it. This is what we get. Now let's compare this to our other graphs. So we got 0, 0, we got pi over 2, negative 1. Well, let's look at this blue graph compared to my original graph. I'm going to actually see if I can drag it. No, maybe not. Let's group these pieces together. If I plop this over my original, notice it's just this black graph just flips. So, turns out, when you have that original function, which was sine flipped, you just get negative sine. So this graph in blue, the derivative of cosine, turns out is just negative sine. So that's our second derivative that we learned. The derivative of cosine is just the opposite of sine. All right, now knowing that, we can take the derivatives of these functions, like y is equal to 2 sine x. Take the derivative with respect to x of this y, giving me dy dx. Using the constant times a function rule, I know I would just leave my constant, take the derivative of my function, and there you have it, 2 cos x. Now if I have y equals sine over 2, well, I would probably rewrite this as 1/2 times sine, and then taking the derivative with respect to x of that. I could either write it's y prime, dy dx, or y prime. Leave the constant, derivative of sine, cos. Let's take q's and r's. I would take the derivative of q with respect to r. This would give us dq dr, which is like q prime. And that would be equal to the derivative of r. That's like the derivative of x. It's just 1. The derivative of cosine is negative sine. Okay, so it would be the same for both. Doesn't matter how you write it. A couple applications. Find the x values at which the graph of the function y equals x plus sine x has a horizontal tangent line in the interval. So horizontal tangent line is when the slope is equal to 0. So I'm figuring out when the tangent slopes of x plus sine x equals 0. I would find the derivative to find my tangent slope generator. Y prime is equal to 1 plus cos x. I'm going to figure out when that is equal to 0. Well, for this, we need to isolate cosine and then solve for x. When is cosine negative 1? When x equals pi. So, right there. Now, we talked about physics in last unit. We're going to continue to talk about it. Let's talk about position, x of t, velocity, v of t, acceleration, a of t. So it's going to be really quick. We know that the average velocity would be your change in your position over the change in your time. Okay? Well, guess what? Exact velocity will be the instantaneous change in your position over the instantaneous change in your time. You could think of that as kind of like dx dt, if this was just an x function with t's in it, something like that. Or you could think of that just being x prime. Right? Because if we want instantaneous change, instead of using the delta, you use the d's. So this is the instantaneous change in your position over the instantaneous change of your time. That's just the derivative. Average acceleration, we talked about being the change in your velocity over the change in time. Well, exact would be the instantaneous change in your velocity over the instantaneous change in your time, which is just the same as the derivative of your velocity. Okay, so this relationship, which I'll write down to make it easier to understand, velocity is equal to the derivative of your position. You want to know your exact velocity at a specific time, find the instantaneous change of your position. We kind of talked about that when we introduced tangent lines. You have 2 points really close to each other. That helps you find a great approximation of your velocity at a specific time. Turns out the great approximation becomes the exact value when the 2 points get infinitely close together. And of course, we could say acceleration is just the derivative of velocity. Okay, so we introduced it with average velocity and average acceleration with the change. Now we're using the instantaneous changes of things, which are just derivatives. All right? So we could have a quick question dealing with a position function. This is the free-falling position function of a diver who jumps off a 50-meter platform with an initial upward velocity of 3 meters per second is this. This is x of t. This is your position, where he's located. This is after t seconds. If you want to find his velocity when t is equal to 1, you can take the derivative of your position and evaluate that at 1. Negative 32t plus 3. Plug in 1. I get negative 32 plus 3, which is negative 29 meters per second, which seems steep, but I guess that's right. We can find the instantaneous acceleration by finding the acceleration function, which will be just the derivative of your velocity function. Velocity function was negative 32t plus 3. Acceleration function would just be negative 32. Turns out your acceleration at 1 or at any value would be negative 32. All right, that's all I got. Good luck on your homework. Rewatch the rest of this video if you have any questions. Hopefully you'll do okay. And I gave you enough examples for everything. Thanks.